divide this on the records, if that makes money to the kids.
Right.
Okay.
Set.
Real selfish, right?
Okay, my little money to feed myself. Get out. All right.
All right? Okay, so meta-analysis. So overall, it's quantitatively combining and analyzing results from multiple studies. It analyzes effect sizes and draws conclusions about overall effect across studies.
Analyzes what?
Analyzes effect sizes, and draws conclusion about overall effect across studies. Results of each study are translated into a common metric. So that's the Hedges G, the Cohen's D.
What about a C or K?
And
Yeah.
I was going to say, we both have written down, it was created by Gene Glass, or coined, the term was coined by Gene Glass in 1976. Just saying. You know the last time he asked you? Yeah. Like,
We never talked about that
people.
book. We never talked about that book. That was about the exam last week.
Well,
He gave you some really terrible choices.
Oh, yeah.
I mean, yeah, but that's like
The Smith and Weston one.
yeah.
And he pulled that crap with us last year, too. I can't believe we forgot about it.
Jan, remember that for next semester? Remember that for next semester?
Yeah. So effect sizes, we don't want to use omega or etas. So there's an equation to convert them. You don't need to know it. But the effect sizes in a meta-analysis become the dV.
The what?
The effect sizes in a meta-analysis are the dV. So the effect sizes from each study become the dV in the meta-analysis.
You guys remember he was talking about this with Dr. Ellison, likes to do these, and he said it's maybe not a very easy dissertation topic because we're constantly tracking back studies. This is that topic.
So Cohen's D, you remember you want to go over the values for what a small, medium, and large effect size is. So Cohen's D is continuous, interpreted in standard deviation units. Small Cohen's D is about a 0.20.
2.0?
Yeah, or less.
0.20. Thank you.
A medium is 0.50.
Let me ask you on the test, I recall him putting 0.33 as a large.
That was for
Yeah. So each of these types of measurements are going to have different ranges of what small, medium, and large. And then a large is anything greater than a 0.8. Do you remember on the handout that he gave you from last time when he was talking about meta-analysis? Let me try and pull it up. This, where it had the list of the studies and the Hedges G and the p-values. Familiarize yourself with this, because this will probably show up on the exam, like a table, something like this.
You give that out last time?
I don't have
I feel like it
anything.
was in some big table big.
Mm-hmm.
I feel like it was in a big package.
It was, yeah. Hedges G is continuous. It's more sensitive Than Cohen's d, yes. It's preferred because it's more accurate since it takes into account variance.
But
And there are no ranges on that.
Wait,
Oh, you do?
it takes into account
The
what?
ranges I have, less than 0.5 is small. 0.5 to 1 is good. And greater than 1 is better.
Can you go back and say it's more accurate because it takes into account what?
Takes into account variance. So Hedges G is more preferred than Cohen's D. Okay, and both of these, Hedges G and Cohen's D, are reported or can be reported in standard deviation units.
it takes into account variance.
Yep, the Hedges G. So that's why we tend to look at one better.
It can be interpreted in standard deviation units.
Okay, and again, those are continuous outcomes. You got everything? All right, you guys got that? So odds ratio. This is dichotomous. Okay, so an example would be saying like the odds of the success in the treatment group relative to the odds of success in the control group. Usually these are naturally occurring groups. Naturally occurring groups. Do you have anything else for this one? Okay. And then correlation coefficients. It's the strength of association between two continuous measures. It can be used as a Pearson's R or odds ratio. Okay, and 0.1 is small, 0.25 is moderate, and 0.4 is large. Okay? Moderate was 0.25, and 0.4 is large.
And it's the strength of correlation between two continuous variables.
Measures.
Yeah.
Just one final note on effect sizes. They don't take into account context of the intervention. Yeah, they do not take into account the context of the intervention. Context. An interpretation must be done within the bounds of the methodological quality of the research being synthesized. Huh? So interpretation must be done within the bounds of the methodological quality of the research being synthesized.
Okay, cool. So with inclusion and exclusion, you want a balance. Okay, so this is when he was talking about how do you know which studies to use for your meta-analysis. So inclusion, you want to be as inclusive as possible. So find all the studies you can, even the ones that were unpublished. Okay, so even though they didn't come to statistical significance, so typically they're not published, you still want to include those because those are important findings. And then for exclusion, you exclude studies that are methodologically unsound. Right, because you can't count on those findings to really mean something true. Yep, so exclusion, you exclude methodologically unsound studies. Okay, so when we're talking about bias, this is referring to how those significant studies are more likely the ones to be published. So this poses a selection bias. Okay, and again, there are many non-significant findings that are not published, but those are still important findings.
How do you find them? They weren't published.
Dissertations are usually the ones that aren't published, or if there's an author that does research in a specific domain, you may email them and say, do you have any articles that you've done on this topic that you haven't published?
Why aren't dissertations published?
Because if a lot of times we don't find anything, and then there's nothing to be published because people typically only want to read when you have a significant finding. And it's obviously for dissertation, it's okay if you don't find something. That happens a lot.
Not finding.
Yeah.
Blue light. That's blue light.
Okay, so types of studies. We just have a long list. So, are you guys ready? Okay. Computerized bibliographic databases. Number 2, authors working in the research domain. Number 3, conference programs. 4, dissertations. 5, review articles. 6, reference lists. 7, hand searching relevant journals. And 8, government reports, bibliographies, and clearinghouse houses.
Also, another place to find unpublished studies potentially is poster presentations, so like conference abstracts, because those usually have papers and full research studies that go along with it. So they may have made it to poster stage and been accepted in a poster conference, but not necessarily then published. So. And then he has apples and oranges as a concept list item. Basically, it means you need to compare things that are similar and not try to compare things that are so completely dissimilar is the idea behind it. But it's not completely objective in how we decide what to include and exclude.
He says it's in the eye of the beholder. The eye of the beholder. So as the one doing the meta-analysis, you may decide what's appropriate to compare. You know, the next person may think that those aren't appropriate comparisons to be making.
Right.
And then as you go along in your meta-analysis, you can revise your criteria if you're finding that things aren't matching up. And do you have strengths and weaknesses?
Yeah. Okay, good. So strengths of a meta-analysis, it sums up research findings. It sums up findings in a differentiated and sophisticated manner more than just a review of the literature.
Supposed to be some regular literature.
Can find relationships among obscure studies. Protects against overinterpretation. And can handle a large number of studies. And then some of the weaknesses. It requires a lot of effort. It doesn't capture the qualitative distinction among studies. Comparability of studies is somewhat subjective. Again, it depends on what you've decided is your inclusion and exclusion criteria. Comparabilities of studies is subjective.
Like the apples and oranges.
It includes blemish studies.
What are those?
Like studies where there may have been violations. These are usually the things that are found in unpublished studies. Maybe they weren't, obviously something that's been submitted to a peer-reviewed journal has had the statistical analysis, then questioned and combed through, was it appropriate, was it not? Unpublished studies aren't going to have that. So it may not have been an appropriate type of statistical procedure that was run on it, something like that. Selection bias is a threat. You can't always find everything. Or you can email authors and they just will never email you back. An analysis of between studies differences is fundamentally a correlation. Yeah, analysis of between study differences is fundamentally a correlation. So Manova, right? And we went over ROC last time, and that was on the exam last time, correct?
So all of that is analysis.
Yeah.
It's not conceptually too bad. It's just some memorizing.
Okay. So Manova, well, the reason you do it is 1 dB seldom captures the whole picture. As a correction for type 1 error, this is the heading. And basically, Manova provides control for making a type 1 error rate that would occur by doing multiple ANOVAs where the DVs correlate.
Provides control for?
Yeah. So doing a Manova corrects for making a type 1 error that would occur by doing multiple ANOVAs, especially where the DVs correlate. And this is also known as probability pyramiding. Although I don't think you'll see that on the exam, that word.
Probability correlating.
Probability pyramiding. So other uses for a Manova. It's best when the DVs are moderately correlated. So a range of 0.3 to 0.5 is good. It's like the Goldilocks analogy. You don't want the DVs to be too independent or if there's too much multicollinearity.
That's what the test is for finding that 0.3 or 0.4.
Yeah, you can look at the correlation, so you can even just run a Pearson R with just the DVs. You can also identify the DV that best captures the variability between the levels of the IV by running a Manova. You can identify the DV or DVs that best capture the variability between the levels of an IV. So the sample size needed, you need a minimum sample size is the number of cases per cell must exceed the number of DVs. And then I also have that you must need at least 20 cases per cell to achieve minimum levels of power. Yeah. Must have at least 20 cases per cell to achieve minimum levels of power.
Okay, so Manova versus repeated measures. So repeated measures, the same considerations as within subjects ANOVA. So you need to assess first sphericity. Okay. So repeated measures, it's basically the second one down. Same considerations as within subjects ANOVA. So you need to assess for sphericity. Do you guys remember what that was? Sphericity?
Remember what the concept is and overcome the test for it.
Yeah, when all the participants' data points stay in the same relative order. Okay.
Cycles on no effects at all.
Mm-hmm.
What's the test for sphericity?
Matrices. Mauchly. Yeah, Mauchly. I don't know.
I like it pronounced with the C.
Does it say that like
Sounds like macho.
sphericity of the whole thing?
Huh?
Yeah, it does.
Right.
So they don't really have to know. So it gives you an epsilon value. 1 means it's not violated. If it is violated, then you want to look at the Hunfeld score. Okay, so another thing about repeated measures, that there are some advantages. So you need fewer subjects. You can get more power because you have lower within group variance. Yep, higher power because you have lower within group variance. If you guys remember what the power equation is. Okay, and it ignores between subject variance. And that's because the participants are compared to themselves. All right, so next bullet, synthetic variables. Next concept. These are also called latent variables, which you guys probably remember. They're also called variates.
Latent variables is the latent variables?
Uh-huh. Or variates.
Well, I'm sorry, can you repeat those three?
Synthetic variable, latent variable, or just the word variate.
Variate.
Variate. V-A-R-I-A-T-E.
Variate.
So in Manova, the DVs are combined into a weighted linear composite.
We'll weight it.
A weighted linear composite. Okay, and your target is the IV. What does it mean? The next sentence.
I don't know.
Okay, wait, let me forget. Okay. All right, so regarding assumptions, I know some of you have been expressing concern over how many assumptions there are throughout all the units and what they are. It seems like he really does want you to be able to differentiate different types of statistical analysis and their different assumptions. I don't know if you guys work together, but I would suggest getting a couple people, breaking up the different units, and just making like a summary sheet or table, just to have it all in one place. That might be helpful for when you're studying. So, just a suggestion if you haven't done it. Yeah.
Question on the last one. When you said DVs are combined into weighted linear composite, is that tied in with the assumption multivariate normality? Like, is that composite what we would look to see?
No, this is the weighted linear composite this is like the factor loading piece where items load on individual factors and then you create a whole overall name for it.
All right, so do you guys know what the assumptions are for Manova?
All of them.
All of them.
Of observation.
Okay, so independence of observation. Good. So how do you test that? Durbin-Watson, and what's the range? 1.3 to 2.7. Okay. Next assumption, what is it? Univariate normality. Okay, so this is when you want sort of like a bell shape. Okay, what test can you look at? Yep, the Smirnov test. And do you or do you not want significance? You do not want significance. If it is significant, it is violated. Okay, you can also, remember when we do the descriptives, you can look at the skewness and kurtosis values as well. And you want less than plus or minus 2.
Durbin-Watson, you do not want significant either, right?
Durbin-Watson is a range.
The 1.3
Okay.
to 2.7.
You said you want less than or greater than?
You want less than plus or minus 2. So between those values. All right, what's next?
Homogeneity of variance.
And what's the test for this? Levine's. And do you want significance or not? No significance.
Remember, violations of this test increase the chance of making a type 1 error. Homogeneity of variance is the similarity of distributions. It's the spread or width of distributions is roughly the same. It also assesses within group variance.
Okay, the next one, linearity. Okay, so between your DVs, you want that straight line relationship. And if you have a curvy linear relationship, it could give you type 2 error. Okay, next is multivariate normality. So do you guys know the shape that's appropriate for this? It's the
Cigar.
Like a half circle graph.
it's the cigar shape.
Cigar shape
Mhm.
for multi-normality.
Multivariate normality, yep. And you find this cigar shape in the scatter plot. And this looks at subjects as a whole. Okay, and then homogeneity of variance, another assumption. Well, it's homogeneity of variance, covariance matrices. Okay, and the test for this is the box is M. Okay, and what about significance? Do we want it or not? No. We do not want significance. Okay, this is just like the test of homogeneity in ANOVA. If you're confused, you can go back. Let's see.
Thank you.
And if you get a violation of this, but your sample sizes are pretty equal, the consequences of this are fairly small. So when your sample sizes are pretty equal, this isn't a huge deal if it's violated.
So if you look at the sample sizes in comparison with each other.
Mm-hmm. And then I said that you can fix this by, or Amber said, that you can fix this by transforming the DVs. So like doing the log. The next thing's important. How do you say it?
Flies, I don't know.
Okay, and then, so let's say you take the log, you do the
Fillets.
transformation, you still have violations, then you need to report it's spelled P-I-L-L-A-I-S. Have you talked about that? Plies. Okay, I'm sure you've seen on the output. So P-I-L-L-A-I apostrophe S. Okay.
Of the four, yeah.
Yep, so this is used to look at these multivariate effects when you have a violation of this variance. Okay, let's see, what else do we have to do?
So if it's a repeated measures Manova, means you have to add in sphericity assumption. Anytime there's a repeated measures anything, sphericity always becomes your assumption you add onto it. Yeah. Anytime you add on a repeated measures, your sphericity becomes a natural assumption. Again, that's saying the same thing. It means the same thing across no matter what study you're applying it to. It's basically that participants stay in the same relative order. And Mauchly's test of sphericity, we don't want it to be significant. Report it Hunefeld to adjust for if you have violations.
What did you say after same relative order?
Huh?
What did you say after same relative order?
That you want the participants to stay in the same relative order.
And then after?
What's
I'm
up?
so sorry. I just need. Are you still filming?
Yes.
Okay, sorry.
I told her to do later.
Sorry.
So if it's violated, you want to report the common value?
Hunefeld, yeah.
So Moxley is not significant.
Yes. Non-significant Matrices means it's not violated. So assumptions for Manova.
Specific Manova.
Yeah, specifically to Manova. Remember, you need to, because you've got the covariate, you need to now look at the relationship of the covariate between all of these factors. So you want linearity between the CV and the DV.
So the relationship between the covariance?
And the DV.
And all of the other, yeah. So the assumption is linearity between the CV and DV.
It's at the bottom of Manova.
Yeah, it's at the bottom of Manova. Homogeneity of the slope between the CV and the DV. So you basically want the CV and the DV behaving the same across all levels of the IV.
That's homogeneity of differential.
Yes. Okay. So Wilks lambda. It tests the significance of the function. Lower values are more significant. Wilks lambda tells you the percent of variance not explained. And so if your variance is r squared, then your Wilks lambda is 1 minus r squared.
Can you say that last part again?
Yeah, it's the percent of variance not explained. And since r squared is your variance explained in the model, then your Wilks lambda is going to be 1 minus r squared.
And it tests what?
It tests the significance of the function.
Okay, so again, the plays with the P. The plies, we sort of referenced it earlier with boxes M. It's right on the list. So this is the sum of explained variances on the discriminant or latent variables. Okay, the reason we referenced it before is because it is more robust to violations.
Can you repeat the first part?
It's the sum of explained variances on the discriminant or latent variables. Okay, and again, you report this when your boxes M is significant. You report this if boxes M is significant. Okay, Hotelling's T squared.
Is this like one of the four that you would report, like Elijah, Roy's, Wilkes, Tellings, because you have a significant boxes and you want to put all of those, or just
No, these are the differences between all of them. So if you have a significant boxes M, then you choose to report.
What?
Flies.
Exactly. So each of these output, they're going to give you, they're comparing or looking at different things. So you report them in different situations.
If you're confused, just check out the output just so you recognize like where to find these terms in the output. So Hotelling's t squared is converted to an f in Manova.
In Manova?
And it assesses between and within group variability.
So think of these as like the multivariate outliers. Remember how there's the Cook's one and there's the Mahalobi distancer and the DF beta and how they looked at all different things? These are kind of the same way. They look at slight variations of the same concept.
So what was the first part of that? Converted to?
F in Manova.
And if you remember the name,
They're all right next to each other. Yeah.
so tell us assesses between group variance.
Between and within group variability, yeah. Okay, and then Roy's. Okay, so this is based on the first or the most dominant discriminant root or latent variable.
Root?
Because it's called Roy's largest root. This is sensitive to violations of homogeneity of variance, covariance matrices.
Sensitive to violation of?
The assumption of homogeneity of variance, covariance matrices. So this one, if you violate that, this test is sensitive to that violation. Okay, and this test is pretty likely to be sensitive, or pretty likely to be significant. Okay, it's the most powerful and the most sensitive.
I thought they said that violate whatever is the most sensitive.
That's for something different.
What?
That's most robust to violations with boxes M. What are we talking about?
So with Roy's,
Roy's.
the purpose of it is to tell whether or not you have a violation of homogeneity or covariance matrices.
No, it's just saying it's sensitive to violations of that. So your boxes M will tell you if you have a violation of the homogeneity of variance covariance matrices
From Manova.
from Manova.
And that's, because I just remember boxes M was discussed as being sensitive but not specific, except for Manova, it is kind of specific to variance, homogeneity of variance covariance matrices. Indicate out of there.
And normality,
Okay, so
It tests multiple things,
homogeneity
yeah.
of variance.
what's the function of
Roy's is if you have one, like again, it's going to test the most dominant discriminant or latent variable. So if you wanted to maybe reduce the size and the number of DVs that you were doing, you can. Yes, there's a significance of value associated with Roy's, Hotelling's, and
Right.
like.
Do we do that enough?
Yeah, I think so. So again, boxes M is very sensitive to violations of, well, just violations, period. It tests normality, homogeneity of variance, covariance matrices. So if you have a significant boxes M, these are all areas you need to look at to figure out where the violation is occurring.
The test in normality.
Normality, homogeneity of variance, and homogeneity of variance covariance matrices. So if you have a violation on any one of those individual tests, Levine's, your normality distributions, it's going to show up at boxes M as being significant. Did he go over the long determinants? I don't feel like he spent a whole lot of time on it.
I won't be in.
No?
Right?
I think so. Okay, well, so he didn't go over this, so I'm just going to tell you just in case it does happen to pop up. If significant, you can look at the log determinants to evaluate homogeneity of variance covariance matrices. I think he did the, what was it called? SPCC matrix when you were checking your options. This would also look at that. But there's another way that he taught us last semester with some log determinants. But basically you want to make sure your DVs pretty much stay roughly equal, like within correlations. You remember that box matrix that he did? You want to analyze that. Okay. So that's it.
That's not even on.
Yeah. Okay. All right. I think that's all the new material, right? He went over ANCOVA last time on the last exam. Okay. And then factor analysis, he went over. Okay. So
Definitely go through your output. I would go through one for every unit you guys have covered this semester, just to refresh your memory of what things look like, where to find them, what values mean. Make sure you go over those assumptions. If you have written down questions maybe that you got wrong on the test, I know you were asking about your old tests. If you want to go over those, we can. You just have to give us a heads up because we're not here every day.
and we have to get the exams from him. We don't have those.
Is it the same thing with last semester? Like if you did well on a certain concept on the final and on the back unit test?
He takes it into account. Mm-hmm. Yeah, because if you fail like a particular unit and then you don't do well in the final, it basically is like a gap in your knowledge. So takes, he looks into that. But if you show that on the final you've covered it, then it should be okay. Doesn't mean that your grade will necessarily go up so much, but at least he doesn't have to tell you. You have to redo that.
And it'll be right around like 30 questions or so for this, for the output section, right?
I remember last time I was annoyed, I remember for the final, because I really studied the new stuff a lot.
Oh, yeah.
And then it was very little on the new stuff and a lot of review from the whole semester.
Mm-hmm.
So really do go over everything from the semester. The final, I personally did the worst on, but that's just because I had a lot of other exams that day, and I didn't put my time into the right sections. So know the new stuff, but also know the old stuff.
And we'll email him and ask him how many questions are going to be on the exam. He should be able to let us know that, and then we'll send you guys an email.
And maybe he'll say, maybe we could ask, like, are there more new material or old material?
What's the split? 50-50,
Yeah.
60-30.
Yeah, I just remember really heavily studying all this new material, and then because it is a cumulative exam, it was my fault. I didn't,
What we did today, going through the different outputs and stuff.
Yeah, that last
Yeah,
sheet that he
packet
made was
seems
great
Amazing.
and funny. Huh?
But I'm mad.
Huh?
And Fields chapter.
Yeah, they were good. They were good. Okay. Has anybody started their final exam project? Okay. No. I would highly encourage you to start it before. It will really help on the exam because it does cover all of it. So even if you go in and test assumptions, and that's all you get through is testing the assumptions for each one before you make decisions, running preliminary exams, that should take you maybe an hour and a half just to run through them really quickly, even if you don't do everything perfectly. Just so you kind of familiarize yourself with everything. You review outputs, what they look like, where to look for the assumptions, that kind of thing. So, and then worry about write-up after the exam. If you have questions, feel free to email us. But again,
Don't forget to review your outliers.
yeah.
Do you have our homework and stuff?
I think I have a couple in my other folder. I'm coming back later on this evening, so what I'll do is I can put them in your box. And you guys are in the... Yeah, okay.